Good morning, everyone. Happy Friday. We're glad to have you join us for the STEMnet webcast series. I'm your host, Jennifer Wicks, behind the scenes. Happy to support the STEMnet team at the Office of the Chancellor in offering this incredible series throughout our system. Today is the NSF Geo Directorate Programs and CSU Awardees session, and we're extremely happy to have all of our guests today to present their work to you. I'd like to make sure that we do capture which campus you're joining from today. If you could put your answer into the poll at the bottom of the screen. We also look forward to your engagement throughout this session in that chat pod. Please enter your questions there. We'll have Q&A after each presenter speaks today, and look forward to all that is to come. So with that, I'm going to go ahead and introduce our moderator today, Dr. Frank A. Gomez, Executive Director of STEMnet at the Office of the Chancellor. Dr. Gomez.
Thank you, Jennifer, for the kind introduction and a warm welcome to all of you. I hope you and your families are all healthy and safe. It is great that you can join us today for a webcast on NSF Geo Directorate programs and CSU awardees. This marks STEMnet's 22nd webcast to the CSU community. From subtle changes in geochemistry to massive volcanoes, the geologic wonders of the world never cease to amaze. The natural wonders of the world are important for their relevance to the discipline of geology and to the awesome beauty that exudes from them. Today, we hope to provide a glimpse to those that have interest in either or both by bringing together representatives from the NSF and the Directorate of Geosciences, and colleagues from across the CSU have received funding for their work in geosciences research and education. The Geo Directorate supports basic research that advances the frontiers of knowledge and drives technological innovation while improving our understanding of the many processes that affect the global environment. These processes include the role of the atmosphere and oceans in climate, the planetary water cycle, and ocean acidification. Supports provided for interdisciplinary studies that contribute directly to national research priorities, such as understanding observing capabilities to support ecosystem-based management and understanding future availability of fresh water. Lives are saved and property is preserved through better prediction and understanding of natural environmental hazards such as earthquakes, tornadoes, hurricanes, tsunamis, drought, and solar storms. Basic research supported by GEO enables preparation for and subsequent mitigation of or adaptation to the effects of these and other disruptive natural events. Today, we highlight several grantees from the CSU funded in the geosciences. Before we begin, I want to remind the audience to use the open chat box on their screens to type in their questions. Our speakers, when not presenting, will make every effort to respond in real time. So let's begin. It is with great pleasure to introduce Dr. Jennifer Wenner, Program Director, Education and Human Resources, Petrology and Geochemistry, Division of Earth Sciences, and Dr. Laura Lautz, Program Director, Hydrologic Sciences, also Division of Earth Sciences, both from the Geoscience Directorate of the National Science Foundation. Jennifer and Laura, the floor is yours.
Hi. Jennifer, I need my presentation. I'm not seeing it here. Is this?
All right, I am bringing it up right now. I realized it was moved to a different location, so I'll have it up in just a moment. If you wouldn't mind starting with just your introduction, I'll have it in just a moment there.
I'm Jen Wenner, and as Frank said, I'm currently serving as a rotating program director in the Division of Earth Sciences at NSF. And I split my time between the education and human resources in EAR and the petrology and geochemistry programs. I'm joined today by Laura Lautz, who is my colleague in hydrologic sciences. She's a permanent program officer, and she's going to be answering questions at the end with me. So today our plan is to talk about a little bit about NSF, about how to find your way in the agency, a little bit about how proposals move through the agency, some of the merit review process, and I'm going to highlight some opportunities across NSF and in particular in the geosciences. And then we'll give you a little bit of advice for people who are thinking about proposing sending proposals to the NSF. So let's dive in. I'm going to start with the agency itself. NSF is a part of the executive branch of the US government, and it is similar to many agencies you may recognize here, like NASA, the USGS, NOAA, and NIH. But relative to many of these agencies, NSF is a pretty small agency, but it has a very big impact due to the low overhead. About 95% of the money that we get from the government goes out the door as grants. And so we have an impact on the sciences pretty regularly. Within NSF, there are 7 directorates that are aligned with different areas of research, and we're going to focus on geo today. So within the Geosciences Directorate, there are 4 divisions: the Earth Sciences, which is where Laura and I are housed, the Ocean Sciences, Polar Programs, Atmospheric and Geospace Sciences. And then within the front office, there's also a portion called ICER, which works with integrative and collaborative education and research. So interdisciplinary and education type programs. Within each directorate, there are a number of sections, and I'm going to focus on the Earth Sciences. In the Earth Sciences, there is the disciplinary program section, which houses 7 disciplinary programs. And then there's the integrated activities section, which houses 6 programs. And the reason I'm highlighting the programs is that is where you are likely to apply for funding. And so I'm going to talk a little bit about how to find funding opportunities within NSF. One way to do that is to just go to www.nsf.gov and find the directorate that you fit and look at the programs and the sections within and the divisions within there. You can also search on the website. If you scroll down the page www.nsf.gov, you'll find this little box that says funding opportunities, and you can search on a key term, or you can look at the programs that have funding available at the moment. You can also do a second way to find where your research fits if you're not sure which directorate or which division, is to search awards that have been made by NSF. And so if you're looking for funded projects, you can look for something that is similar to what you want to propose on a similar topic or with similar approaches. And when you search the awards, what you'll find is who's funded that kind of research before. You can read the abstracts and other items that include the people you should talk to within the programs. And that can all be helpful in finding the right fit for your research. Once you've found where you want to submit, what comes next? Well, there are a couple of important documents that you should know about. The first is the Proposal and Awards Policies and Procedures Guide, which is known as the PAPG at NSF. And this particular document provides guidance. It describes the process of applying and award management, and it's updated annually. So each year there's a new publication, and NSF comes out with a new, and that starts in the fiscal year, which starts in October. The other document you should become familiar with is the solicitation. These are generally the documents to which you'll respond for funding. Each solicitation contains all kinds of important information, including deadlines or target dates. And you'll note that this particular one I'm highlighting, which is the petrology geochemistry one, has no deadline, and we've gone to that for a variety of reasons. It also highlights what kinds of proposals are accepted, the people you should talk to, funding limitations, and expected number of awards. This is your guide to writing a proposal that fits in the program you want to apply to. So read it very closely. There are often also frequently asked questions associated with each solicitation. There are a few other mechanisms by which you can apply, for example, dear colleague letters, workshop proposals, or other short-term calls for proposals. But most proposals are submitted under a solicitation. And once you become familiar with the solicitation, you're probably ready to compose a proposal. So I'm going to talk next a little bit about what happens to your proposal once it gets to NSF. So you've submitted your proposal through research.gov, and it first goes to a program director or the program for a compliance check. A compliance check means, did you follow the directions in the solicitation? After that compliance check, there are a couple of things that can happen. The first thing that can happen is if you haven't paid enough attention to the solicitation and it doesn't pass the compliance check, it can be returned without review, or if it doesn't fit in the program. Or it moves on to the merit review portion of the process. And that merit review process involves ad hoc and or panel review. And in the earth sciences, we mostly do both of those things. But we need 3 pieces of input in order to move forward. After merit review, the program director makes a recommendation about whether to fund it. We weigh a number of factors, which include the results of the review process, the potentially transformative nature of the work, demographics, institution type, geography, PI career stage, etc. And this decision can be to recommend award or decline. Once the program officer has decided to do that, we write a review analysis and forward the recommendation to the division director. If it's declined, it goes back to the organization. If the decision is to award, the proposal goes to the Division of Grants and Agreements, or DGA, and they award the proposal. And that can actually take about 30 days, but eventually the award will make it to you and you'll be funded. The NSF runs the gold standard of merit review, and most programs in EAR, as I mentioned, use a combination of ad hoc and panel, which means that we have to ask quite a number of people to review every proposal. It may be 6 to 10 people per proposal, and then at least 10 people for a panel. So we have many people that need to be involved in the process. If we have 100 proposals, that can be at least 600 people that we have to ask to review for one program for one deadline in one program. So if you have the capacity to do so, we ask you to volunteer to be a reviewer. We would love to see you review some of the proposals. The merit review process involves 2 criteria, intellectual merit and broader impacts. And we ask that reviewers review the proposal thinking about the 5 questions below for both of these criteria. And so they eventually give it a ranking. And I want to talk just a little bit about the broader impacts because many folks struggle with broader impacts. How will your science impact and benefit society is essentially the question you want to ask. And so on the screen there are several, but by no means all of the categories of broader impacts. And most PIs can find ways to touch on at least one of these. Keep in mind, though, that proposals that do well do not try to cover all of these. They find something that is well suited to their work, their expertise, and or their institution. And the broader impacts are well integrated and meaningful parts of the science. They're not superficial and tacked on to satisfy their requirement. Next, I would like to highlight some of the programs that might be of interest to folks. And I'm not going to go into a great deal into great detail on these, and I'm going to share these slides with the links on them so you can explore them more at your leisure. For graduate students, you may want to highlight, and undergraduates, you may want to highlight the Graduate Research Fellowship Program. And those can be applied for by undergraduates and graduate students. For graduating PhD students, The postdoctoral research fellowship is available in all of the different directorates of the geosciences. So AGS, EAR, OCE, and OPP. There's also research experiences for undergraduates, which can be for undergraduates, but also the faculty may wish to apply for that. And then also the mid-career advancement, which aims to advance the research programs of those at the associate professor or equivalent rank. For folks that are early career faculty, there's the career solicitation, which is designed to be a prestigious award and must effectively integrate research and education. And there are special review criteria that proposers and reviewers must pay attention to. They're single investigator proposals, and they must be sanctioned by the university. They are submitted to the disciplinary programs that they fit with. And then just a few opportunities across Geo and NSF. The Mid-Scale Research Infrastructure Program supports the design or implementation of unique and compelling research infrastructure projects. The Research Opportunity Awards enable faculty members at primarily undergraduate institutions to serve as visiting scientists at NSF-supported with NSF-supported PIs. GeoPaths addresses barriers that some historically excluded groups face in entering the geosciences, and NSF Includes, which builds alliances for systemic change. Finally, to wrap up, I'd just like to summarize a little bit of advice for proposers. We encourage you to sign up for automated emails from NSF about a variety of things. You can do that on the page for the geosciences. Make sure you read through the program solicitation and frequently ask questions before contacting program officers. Volunteer to review proposals. It's a great way to learn how to write proposals. And to do that, you can email your NSF program officer to volunteer. And finally, visit the Grants Conference Resource Center for more about the process. We also invite you to join us for a more detailed Navigating NSF virtual workshop at AGU in a little over a week. And Laura's actually going to be leading that particular workshop. So I just want to thank you for your attention. And I think Laura and I would be happy to answer any questions. Thanks.
Thank you, Jennifer. Thank you, Laura. Very, very informative presentation. And certainly, I can speak for myself, these calls, some of them not having due dates, is most appreciated. I found that not only for me, but a lot of faculty who don't have to stress out as much with kind of working back a timeline. But with that in mind, though, how has this been affecting the review process and timeline? And also, is there an ideal time to submit proposals? I'll address this to Laura.
Thanks, Frank. That's a good question. And it's true that removing deadlines can be very helpful. It also means that sometimes it actually can be almost a bigger challenge to actually force yourself to submit that proposal. So, submission rates have dropped a little bit because of the removal of the deadline. But that's great because of the reviewer load that Jen talked about a bit in the presentation. So I think Jen did a really nice job outlining the reviewer process. And essentially, the removal of the deadlines hasn't changed the review process itself, but it does throw the timing into a little bit more of an open-ended timeline. So basically, for earth sciences, as Jen mentioned, we do ad hoc and panel review. So all proposals will go to a panel. And many programs still host 2 panels a year. Not all, but some, especially the disciplinary programs. And so in a sense, the timeline for review is similar to what it was before, just without the hard deadlines for submission. So often it's still appropriate to target submitting proposals in the late spring or early summer, or the late fall, early winter, but it's really dependent on the program. And so, you can of course submit proposals anytime. There's no desired time to submit them. But if you're curious about when panels are or how that might affect your particular proposal, I would encourage people to reach out to a program officer and say, hey, I'm thinking about submitting a proposal at this time. Is that a reasonable time for panel? And we can clue you in if you're pushing up against a soft internal deadline for getting that proposal to panel.
Great, thank you, Laura. I think this one would be most apropos for Jennifer. How does NSF review interdisciplinary proposals that go beyond a single program?
That's a really good question as well. And I think that most program officers are really dedicated to making sure that we find a home for all the proposals that come into NSF. And so if you think you have a proposal that fits in more than one program, you can reach out to your program officer and ask if it is appropriate for their particular program. But we also often share proposals between programs. So, for example, Laura's program and the petrology and geochemistry program share a lot of times like things that deal with water and volcanology, because she's in the hydrologic sciences. And so we share these proposals, we co-review them in panels, and the program officers listen to the discussions, and we often co-fund them. And so it is perfectly acceptable to reach out and ask, does this fit in your program? And we may say yes, but we also think you should reach out to the hydrologic sciences or geophysics or something like that, and see if they would be interested in reviewing it or co-reviewing it. And we may say, well, it's more fitting for one program, but we'd be happy to co-review. So you can actually indicate more than one program when you submit it. Usually 2 is good, but we will sometimes co-review with more than 2 different programs. So we want to find the right place for your proposal, so we are happy to talk to each other and share them.
Thank you, Jennifer. Here's one more question. I'll address it to Laura. And this is always, I won't say always, but frequently a question that I get asked too in my position at the Chancellor's Office. When are letters of collaboration appropriate or needed for a proposal?
Thanks, Frank. That's a question we get a lot too, and a good one. Letters of collaboration, their purpose is really for individuals who are not listed as a PI or a co-PI or senior personnel in a project to affirm the role that is described for them in the project description. So if there's someone who's going to participate in the research who's not listed as a senior personnel, they could be in the budget, but maybe in a role that's not in a leadership position of that kind, they can provide a letter of collaboration that simply affirms that they will perform the work that's described in the project description. They actually follow a pretty strict format. So they're not a letter of support, they're not a letter of recommendation, they're just a letter of collaboration. So the template simply says, I, Laura Lautz, am going to participate in this proposal as described in the project description. And that is a good thing for reviewers to see, to demonstrate a commitment by the collaborator, especially if they're not listed as senior personnel, right? It shows that they're aware of and have committed to the role that they have been assigned in the project, or it's described in the description.
Thank you. I can almost recite that in my sleep, though. Those sentence or two that just fill in the name and the title of the proposal, all the letters that I've written. So I'd like to say, thank you, to both of you for a very interesting presentation, and certainly for spending some time. Huge audience participation there for answering some of our questions. And if time permits, if you do have time, to stay around for a little bit if anybody does ask you questions in the chat box. So thank you very much, and we look forward to working with you and the whole CSU in the future. So thank you. Our next speaker is Vali Memeti from Cal State Fullerton, and her title is The Temporal and Spatial Behavior of Magma Plumbing Systems as Seen Through the Geochemical and Geochronologic Lens of Minerals. Vali.
Thank you so much, Frank, and thank you for having me here. I am very excited to be part of this webcast and talk about the temporal and spatial behavior of magma plumbing systems as seen through the geochemical and geochronologic lens of minerals. This is what I do. I'm an igneous petrologist and structural geologist, combining both whole rock and single mineral geochemistry combined with zircon, uranium-lead zircon geochronology to work on magma plumbing systems and to better understand them. And of course, I don't do this in vacuum. I have collaborators at Sac State, Texas Tech, USC, and Princeton University at the moment. So one of the big picture hypotheses we like to test is what a magma plumbing system and continental volcanic arcs really looks like. And so here's a schematic that sort of shows such a potential magma plumbing system, and the hypothesis that we have is that you start off fairly low volume with fairly heterogeneous compositions of magmas at the beginning, and then over time you build this magma plumbing system that produces a preheated pathway for more voluminous magmas to get through there and then to make it up to the surface and erupt in a volcanic eruption. And as these magma mush columns, as we like to think them as, develop, they also provide these magma storage areas that have active magma in them. And what goes on in such magma chambers and magma storage areas that are insulated by the magma mush is basically the big question that we're trying to answer. And so I work a lot in Yosemite. And in Yosemite, you have the rocks beautifully exposed, and the rocks are very fresh for geochemical analysis. Sorry, this forward a little too quick. And the intrusion, called the Tuolumne Intrusive Complex, where I work in, is very large. It's 1,000 square kilometer exposed plutonic complex. And so in that complex, we think we had something like these hot magma storage areas that then underwent many magma processes through time. There are magma pulses that are coming in, as shown in this cartoon by Reed, 2003, that bring in new magma. We have magma mixing between the incoming magmas and the magmas that are already there, and probably fractional crystallization going on. So there's lots that goes on. And one of the questions we want to answer is, well, at what scale do these processes occur? Do we have these gigantic magma chambers that potentially feed super eruptions at the surface? And so to be able to answer these questions, most recently I've been focusing a lot on mineral chemistry, such as the chemistry done on these K-felspar megacrysts, as you're seeing in the upper right. Those are megacrysts that can be up to 15 centimeters across, and we think that contain a lot of information, and I'll show you in a slide or two an example of what we can do with them. So other minerals we are analyzing and interrogating, as I like to put it, are hornblends and plagioclases as well. Those are rock-forming. Accessory minerals are titanite, zircon, apatite. And we're in particular looking for mineral zoning, because mineral zoning means changes in compositions. And compositions change for a reason. And so we can deduce magma processes from these changes in composition. On the right, you're seeing a CL image, cathodoluminescence image, that's highlighting luminescence of feldspars that are zoned. And so we use these kind of techniques to actually look for where the changes are, what minerals look interesting, what specific grains look interesting, to get concentrations from these minerals quantitatively and then interpret them. The upper right shows a barium map of a potassium feldspar, and notice all these oscillations. We're going back and forth between the concentrations in barium in these various zones. And these are telling us something about either magma pulse input or maybe water changes in the magma or pressure changes in the magma. There are all kinds of ideas that we're trying to work with. The project that I was specifically asked to talk about is our collaborative research project that got funded by NSF called the... I'm having issues here with my slides, I apologize.
Do you want me to try to advance those from my end here, Valley? I don't know if it's stuck for you.
It's not, it is stuck actually. Oh, now it's moving. So I need to go back to the slide that says RUI and the title of the project, please.
Okay, let's see here. Sorry, let me just make sure.
Next.
I'll just move forward. Can you?
Yeah, this one.
Okay, I'll go back one in there. This one here, right?
That's correct. Thank you so much, Jennifer.
Okay, sure.
So the project that was funded by NSF is called Collaborative Research, RUI, which stands for Research at Undergraduate Institutions, examining the temporal, spatial, and geochemical focusing of magmatism during a continental arc flare-up. And so what we try to do here is to feed into this bigger question that I was talking about of how these magma plumbing systems get established. And so what we did here is to evaluate this Tuolumne intrusive complex in Yosemite National Park, which composes most of the rocks there, shown here in these lighter pink colors, and how the surrounding older plutons relate to them, to this inner intrusion. The Tuolumne intrusive complex is a big magma body, about 1,000 square kilometers across. And it appears that, especially with the data we collected, that over time you're collecting more magmas into bigger magma bodies that then are left with a crystal pile from which melts are extracted by having large eruptions erupt at the surface. And so that was basically the big picture here, that we're focusing spatially and temporally over time. This intrusion was active for something like 10 million years, so it's a really long time to have these magmas be around. Now, I want to highlight a couple of examples of how students were involved in this project. One of the students is my graduate student, Melissa Chambers, who worked on uranium-lead zircon geochronology of zircons trapped in these K-feldspar megacrysts as they grew from core to rim. And when we extracted these zircons and analyzed them with uranium-lead geochronology, we determined that the core zircons are older than the rim zircons, and the rim zircons even are older than the ground mass zircons. And we learned two things from that. One is the youngest core zircon is 500,000 years older than the youngest rim zircon, which told us that this K-feldspar took at least 500,000 years to grow to this 7-centimeter size. The other thing we learned about is that the core zircons are more similar to ages from an older intrusive unit compared to the rim and the ground mass zircons, and so which are more similar in age of the youngest zircon ages from the youngest unit. And so we interpreted this to mean that the core actually started growth in an older unit, got transferred into the younger unit. And this is telling us something about bigger masses of interconnected magmas at depth as the arc matured. Since this was an RUI project, I involved about a dozen of undergraduate students in this research as well. And just to highlight a couple, Ryan Bramer, who was also included in this paper by Cal Barnes, one of my colleagues, did a study on these mafic enclaves that you're seeing in the picture. And we tried to figure out if any of the minerals are actually getting transferred into the granodiorite ground mass surrounding these enclaves. And so he did some field work with sampling and petrography and whole rock XRF. Another undergraduate student, John Ayers, he focused a lot on mapping the leucogranites in the Tuolumne, and he also did petrography and whole rock XRF, and he also ended up being my lab assistant. And other students did a lot of lab work as well, but at the very least, they ended up doing some of the field work as well. So the lessons that I've learned from doing this project is that NSF funding allowed me to involve undergraduate and graduate students in all aspects of research, going from field mapping, lab work, data interpretation, all the way to presenting at conferences and even publishing in peer-reviewed publications. Several of my graduate students have published first author papers, and undergraduates have been involved in papers as well, as you just saw. And when there's funding, everyone wins, because not only can I advance my research agenda, the students are involved in state-of-the-art projects as well, and they get the sense of discovery, which is really nice for students. RUIs are great because you write an impact statement and you can emphasize things like, we have a diverse student body. We're a Hispanic serving institution as CSUF. In our department, we have a mandatory senior thesis where we have, where I particularly involved 11 undergraduates, 5 Latinx, 6 female in this project specifically, 3 graduate students, 2 of whom were female. I also highlighted the impact that this has on me as an assistant professor, positive, and being untenured, and I thought that was really, it mattered. And my understanding is also that there are separate dollars set aside for RUIs, but Jennifer and Laura can correct me here if that's not the case, but my understanding is that you're not directly competing with some of the R1s. Other lessons learned is get teaching release time instead of extra summer salary. Extra salary is always nice, but with having big teaching loads, I think getting the release time instead is really helpful to make project progress. Getting graduate student tuition and RA salary in the budgets helps with competing for high caliber grad students, and getting stipends for undergraduate students to be more DEI friendly. A lot of our students are at least part-time working, if not full-time workers, and they need to get the money when they can go out into the field. And if you can provide them with money they can pay their rent with, then you know, it helps them. And it's not just the ones who can afford it to go, who can go out into the field and be in the lab. Include more senior collaborators and collaborators with labs. It's great for student training. And also mentoring. As a young assistant professor, it was helpful for someone to help out, and stick with projects you have good background in. In my opinion, the tenure clock is way too short, and it helps to have to be able to hit the ground running and just expand on a lot of what you already know. And so, because I'm out of time, I'm just jumping to this. One of the broader impacts was that we developed an app with travel stories, and that's a guided audio tour in Yosemite that includes some of our results. And that was also done with students at Cal State Fullerton and our geoscience educator there, with some help from Katie Ardell, who's now at Sac State. And I'll take any questions you might have. Thank you.
Thanks, Vali, for an interesting talk. We have one question here. What do you believe were the main reasons your proposal was funded?
So we had all of these broader impact stuff, including the travel stories, audio tour. I think that was helpful, but also the fact that we were two young female early career researchers, one being a PhD student at USC and myself as an assistant professor at CSUF. And then the fact that we do have a very diverse student community at Cal State Fullerton, including a lot of first generation college students. In terms of intellectual merit, I believe we did a very good job in staying to the point, having clearly testable hypotheses that we said, that we described exactly in how we would actually test them. And I highly recommend that that is done. A lot of words don't necessarily mean that you get funding. It's to be concise and to the point is what matters.
Interesting talk, and if there's any questions in the chat box, we appreciate you staying around. So thank you for participating in the webcast today. Great. Our next speaker is Nate Onderdonk from Cal State Long Beach, and his talk is entitled Doing Active Tectonics Research in SoCal and Strategies for Funding Local Fieldwork. Nate?
Thank you. So I'm going to give a quick summary of an NSF proposal that I had funded a few years ago. This was able to allow me to support 5 graduate students and 5 undergraduate students. And 2 of those graduate students and all of the undergrads were from underrepresented groups in the geosciences. And the goal of this research was to get a better understanding of mountain building processes. And the area that I focused on was the Western Transverse Ranges in Southern California, which is shown in that area with the box around it in the Santa Barbara area. And specifically, I was interested in understanding a little bit more about the deeper deformation that controls the large-scale topographic growth of mountain ranges. So this area is composed of multiple reverse faults and folds, and individual ranges are lifted along those faults. But I noticed that in addition to uplift along in the hanging wall of these reverse faults, there also seemed to be uplift, land rising in the footwalls of those faults, which is not what you would expect from a very simplistic model. So I was curious to investigate this idea that there was a more regional component of mountain building in addition to uplift along individual faults. So to do this, we used terraces, river terraces, throughout the western part of this mountain belt as markers for uplift and deformation. So we used a combination of field mapping along with LiDAR, which is high resolution topographic data collected from laser scanning from an airplane or a drone. We also did GPS surveys of the terrace surfaces to document their exact elevations and how much they had risen above the active rivers. And then we used luminescence dating of terrace deposits to get the dates of these terraces, and that was done here in my lab at Long Beach State. Just an example of the type of data that was generated. This is a map of terraces along the Santa Ynez River near the town of Solvang. The different colors are representing different ages of terraces, with red being the oldest and yellow being the youngest. The numbers in the white boxes are the dates that we obtained from these different terrace levels, and those are in thousands of years. So the oldest ones were around 125,000 years, and the youngest were closer to 30,000 years. So we noticed there was a consistent set of 3 terrace levels throughout the entire area, which was really nice because it allowed us to correlate between drainages and evaluate a whole bunch of faults that hadn't really been studied previously. Had nothing really known about them. And then the GPS surveys allowed us to document the amount of folding or deformation across the faults. So here you're looking at an example of a kind of a cross section of surveys up one of the drainages. And the thing I wanted to point out here is that on the left side you see a purple line. That's the oldest terrace, and you can notice that it's offset along the baseline fault. as well as the next youngest terrace represented by the red line, whereas the youngest one in the orange is not offset by that fault, telling us that this fault has ceased moving and has not moved in the last 70,000 years. And then this GPS data also allowed us to calculate the exact amount of uplift there's been relative to the active rivers that are cutting down as the topography comes up. So some of the lessons that we learned here, first, we kind of confirmed the hypothesis that there is a component of regional uplift throughout the entire area, in addition to uplift along individual structures. So the map I'm showing here is showing the faults in the western part of the mountain belt. Those numbers in the boxes are the rate of uplift in millimeters per year. So some of these are pretty high. You see like number 4 in the middle there and 3 in the southwest. Those are pretty high rates of uplift, even in California. And those were in the hanging walls of some of these faults. But there's also uplift going on in the footwalls, the 0.6 and 0.3 that you see over towards the east a little bit more. So there is a larger component of regional uplift that's also contributing to the growth of the mountain belt. The other thing that we learned is that these faults have not been constant over the last 100,000 years. So what I show here is I have some of the faults highlighted in bolder lines. Those are the faults that were active between 85 and 40,000 years. And if we look a little bit closer in time, between 40,000 years and the present, we see that some of those faults have turned off and other faults have turned on, which was kind of a surprising thing. Over this time scale, you typically wouldn't expect faults to be turning off and on over tens of thousands of years. So this shows that the overall deformation of the area is sort of migrating from different places to other locations in the mountain belt over time. The reasons for that, we believe, is that there's a large detachment that's been hypothesized by numerous previous studies underneath the transverse ranges. So this figure, I'm showing the map in the lower right. There's a black line, which is a cross section that's represented in the upper part. And so we're looking at kind of south on the left of that cross section, north on the right, and there's a series of faults represented by the black lines. So this underlying detachment is supporting, shortening across the area, but we believe that how that deformation is translated up to the surface can change through time. So earlier in the last 100,000 years, it was focused in the Santa Maria Basin over more towards the right of that diagram. And then now more recently, it's been focused towards the south in the Santa Barbara Channel. The next step for this research was we found out that a lot of the areas that have very high uplift rates, where the land is rising fast, also seem to have relatively lower topography compared to the rest of the mountain belt. And then the areas with the highest topography seems to have the slowest uplift rates, which is sort of the opposite of what we would expect. So this is indicating that the topography that we see is not purely a function of how fast the faults are moving and how fast the land is coming up, but there's other processes in operation here as well. And so that's kind of the next step in this project, is to start investigating that. And I had 2 more undergraduates this past summer doing analysis of the topography to investigate the influence of rock type on the overall growth of these mountain ranges over time. So a couple of things I've learned about funding strategies from this grant and previous ones is, local field work is cheap and can fund and involve a lot of students. When I first came to the Cal State system, I'd been doing a lot of work in Arctic geology in Greenland and Arctic Norway, and that was obviously very fun and exciting, but it takes a lot of money. I mean, a helicopter ride is $7,000 an hour, and so if you want to get a lot of students involved, that's not always the easiest route to go. The other thing I've learned is oftentimes you see studies or proposals and it looks like they've come up with a big science question and then found the perfect place to study that. And maybe that's true for some people, but I've found that it's easier to really focus in on something that you're interested in, some area that you're interested in. And almost anywhere, there's going to be some big science questions that sort of fall out of that work. And then you can use that to propose your future work. Then I also have found that proposing work that you're already doing is a big help. I initially thought that I had to come up with a project and propose it, and then if it got funded, I would work on it. But I realized that you need to have some preliminary data to really show the feasibility of the project. So in a sense, I sort of start a project as cheaply as possible, and once it gets going, then I look for the funding to keep it going and really expand it. And along that same lines, there's, at least in my field, there's quite a few small grants that are available that are much easier and faster to apply for than NSF, but they, essentially are seed grants to go after the bigger funding later on. So if these exist in your field, I think that's a great way to get the research started and really get it moving. So, and that's it for my presentation. I'd be happy to answer any questions.
Great, thank Nate for a very, very interesting talk. And there's one, amongst other things, there's one thing that you said in one of your latter slides that was very, very important, where you said go after the small grants because they're easier to get and they add up. In all my career, which spans multiple decades, aside from the bigger ones, which we had our stab at and were successful to an extent, getting a lot of those little ones does add up because several little ones can almost equate to a large one and can fund not only some release time and a lot of students too. So I think that's word from the wise. In terms of a question, you wrote in one of your slides these faults kind of come and go. So doesn't that kind of beg the question then, if they come and go, is there really no place, at least in California, that is really safe to build on, given that if they come and go, you really don't know where's a safe place to build?
Yeah, I think that's actually true to some extent. I mean, there's obviously places in California that have higher earthquake hazards and more rapid tectonic processes than other spots. But, it's funny you mentioned that because oftentimes, some of the other work that I do is incorporated into, state seismic hazard maps and there's often questions from urban planning people, city planners saying, can you just show me a map of where I can build? Because there's fault hazards, there's landslide hazards, there's flooding hazards. And, when you start factoring that in, there's really just a small area where, there's nothing. But yeah, that is true. I mean, I think in this area, this is a very active area with high deformation rates and uplift rates. So it's not unexpected that these faults would be a threat, but that is true for much of California.
Yeah, great. Well, thanks, Nate, for a very, very interesting talk, and certainly in your ability to really integrate a lot of a diverse group of students in your work. So thank you.
Thank you.
So we go back to Rachel Teasdale, and we think her volume's working. So yes,
can we test real
Rachel.
quick and make sure? Can you hear me?
Oh,
yay! Okay,
yours.
Then I'm going to go all the way back. So this work is is a collaborative project like most projects. I'm working with Kathryn Riker at University of South Carolina and Kelsey Bidding at Elon University. And just to recap, we're interested in TA beliefs as they teach introductory geology labs and how those beliefs impact student learning and interest. So this is education-based research. So geoscience education research is very similar to other kinds of hard rock, soft rock, those kinds of areas in geosciences. In education research, we are interested in the methods and theories of teaching and learning. So like all other research, we are testing hypotheses about teaching and learning. So our research questions and the design of our research is similar to other areas of science. And I should say, I also do petrology and volcanology research. So this is one of the areas of my research, but maybe a little bit different than work that other folks have done. When you're doing education research, you are studying humans, and so there's an institutional review board that needs to approve your research design and methods and data collection techniques. This protects the subjects of your research, our students, and also protects them in terms of their privacy and keeping data secure. So that might be an element that some geologists are not familiar with. However, in terms of education research, it certainly can contribute to RTP, that's the tenure and promotion process. At least at Chico, that's our acronym. You can publish this research. There are dozens of journals. The one that is most specific to geoscience education is the Journal of Geoscience Education, which you can see on the in the cartoon there. So this is just another, not just, I shouldn't say just, this is another discipline of the geosciences. So we started this research in spring of 2020, and of course we're immediately faced with everything going online, which was not at all part of our research plan. So we regrouped and figured out ways that we could collect our data using TAs and similar data collection strategies that we had planned for in person, but in the online setting. And these are, I'll remind you, introductory geoscience labs, which many of you have experience with teaching online now, and not the ideal situation, but we think we found a way to make it work. So flexibility, like other research areas, is key. So funding for geoscience education research, ours at least is through NSF, and we were funded, or we currently are funded by the IU's program, so that's Improving Undergraduate STEM Education. And again, I want to emphasize that this is research. This is not release time to develop a new course because your department chair assigned it to you. This is, theories and ideas about the way people learn and trying different theories in terms of how we teach or those kinds of things. So we're building on the body of existing research to advance what we know about teaching and learning. As with all NSF and other solicitations, you want to make sure you read through it very carefully. Jen talked about that when she was talking about NSF programs. Talking to our program officer was also very helpful. And being familiar with the literature that already exists. There's no reason, and it would not be funded if we were just going to do something that had already been done. So all of that advice applies to any program. So I just wanted to let that be known. Okay, so what is our project? We are interested in two sort of areas. One is improving training for TAs and also improving student learning, specifically in intro geoscience lab courses. So we have two research questions that we're using to guide our project. So the first is, how does teaching inquiry-based labs influence geology TAs' beliefs about teaching and learning? And then second, how is student learning influenced by the level of inquiry, the TA beliefs, and also their own interest in the topic? So to do this, we have a plan to collect data for 5 semesters at 5 PhD granting institutions. There are about 21 TAs each semester who are teaching collectively hundreds of students in 7 different courses. And each of those courses, those lab courses, use at least 3 of the inquiry-based labs. So I mentioned that we started in spring of 2020, and that was designed to collect data prior to incorporating the inquiry-based labs. So this is going to be our baseline comparison data. Well, of course, COVID hit, and all the TAs were faced with trying to move online. The students were faced with trying to move online. And so we just decided that there were too many extenuating circumstances. And so we did not collect all the data that we had originally planned in spring of 2020. But in the summer of our first year of the project, we did go ahead and host a virtual workshop through the Earth Educators Rendezvous. And in that workshop, we had about 60 participants who collaborated to create 17 inquiry-based labs. And then in summer of 2021, we hosted another activity where those labs were all peer-reviewed and are now published. And so the link at the bottom of the page takes you to those inquiry-based labs. So then, since then, in fall and spring last year and fall and spring this academic year, we're collecting our data. To understand TA beliefs, we are conducting interviews using the Teaching Beliefs interview protocol. So this is a validated instrument known to accurately collect information about people's beliefs about teaching and learning. And then the student data that we're collecting includes their interest in the labs that they're taking each week. And so they're asked a few very short multiple choice questions about the level of their interest in their weekly labs. And then at the start and end of each semester, they also take a content survey. So we're measuring how much they're learning from their baseline at the start of the semester to the end of the semester. And so these are also multiple choice questions. Some of you may be familiar with the geoscience concept inventory. They're questions like that. So we lost our opportunity to collect reliable data in the spring of 2020. So in order to collect baseline data, we added another course that is not using any inquiry-based labs, but teaching topics that are very similar to the ones that we're testing. So that was our adjustment to being able to have that comparison. All right, so to address our first research question of TA beliefs, we code the interviews that we do, and I can't remember if I mentioned those interviews are done at the start and the end of each semester. So we can look at whether the TA's beliefs actually change over the course of the semester. We code those so we can have a quantitative ranking for their answers to 7 of the questions in the interview protocol. So I had a student work on some of this data. She looked at 2 of the questions. One question is, how do you describe your role as a teacher? And the second question she looked at is, how do you know when learning is occurring in your classroom? And so the pie charts that you see here show the change of the TA responses over the course of one semester, which was last fall. So in gray, you see there was no change. So their answers at the beginning and end of the semester were at the same level of sort of teacher-focused versus student-focused beliefs. The pink or peach color indicates that the TA's beliefs changed, but towards more teacher-centered beliefs. And the green represents when the beliefs changed to more student-centered beliefs. And the difference between teacher-centered and student-centered is in a student-centered classroom, the focus is on student learning and supporting students in their learning. And in a more teacher-centered classroom, or in a more teacher-centered set of beliefs, those beliefs are more focused on the teacher. So if I do this, then that might be helpful or not helpful. Whereas a student-centered set of beliefs would focus more on what the students are doing in terms of their learning. So you can see in the pie charts that TA's ideas of their roles as a teacher were more likely to change than when learning is occurring. We also noticed that TAs who have less teaching experience have more malleable beliefs, and that's something that we've seen in the literature, not so much for TAs, but more for faculty. So this is just an early set of data. I have some more data, but I see my time is really low. So what I want to share with you is this graph shows results from the student interest surveys compared to their learning gains. So that would be how much learning occurred in their content surveys. And you can see that the correlation is not very strong and that the data are all over the place. But when we look at the data on a school by school or a course by course basis, now you can see each color represents a different course, and we do see strong correlations. What's more complex than we expected is that in some cases the correlations are positive. So in the case of the blue dots, we see that interest is positively correlated with learning. In the case of the purple triangles, we see that in that course, interest is not positively, it's actually negatively correlated with learning. And so that's something that we didn't expect. And so we're still continuing to collect data, analyze the data. We have lots of semesters, lots of data for both projects. We were able to develop new research questions along the way, which always happens, of course, in terms of how to support all students, either through inquiry or interest or those kinds of things. And also, one of the tiny shining moments of this COVID is that we now have a great data set comparing online interest in learning last year with in-person interest in learning this year. So I'll stop there and happy to answer any questions.
Thank you, Rachel. Very, very interesting talk, and certainly one in the geosciences education area is also something I'm very, very interested in, given I work with a lot of people in this area. We actually had an RU, I was thinking of an RUI, an IUS funded just within the past month. So we're happy about that, which kind of complements our NSF HSI STEM grant that was funded a couple of months ago too. So it's nice to see that you got one of these funded. Question, and this is something that certainly a lot of the faculty in the CSU would be very interested in knowing. How does educational research contribute to your progress through the RTP process?
Yeah, I think that's really important because in the CSU, you know, we're somewhat unique in that we have a very high teaching load, and I know for myself and many colleagues who I talk to, we don't have a lot or didn't have a lot of training in teaching. And so I think there's two aspects of education research contributing to RTP, and that is that you know, it's part of my research and part of my publication record. So it's part of my scholarly work that I submit in my dossiers when I turn in my, you know, tenure or promotion package. You know, these are publications that I list in addition to those in petrology and volcanology. But also a more, I don't want to rank them, but anyway, another important aspect to this research is I'm actually learning what's cutting edge research in the classroom, and I can apply the results of this research to my own classroom. And so as we're learning more about inquiry labs, I'll be able to be better positioned to know what kinds of changes I might want to make to the geology labs that my TAs are teaching. So there's a twofold benefit to this to me. I become a better teacher and can support my students in their learning better, but it's also part of the way that I'm ranked in terms of my scholarly work.
Interesting talk, and look forward to hearing more from you in the future. So our next speaker is Kathryn. I think she goes by Kate Metcalf from Cal State Fullerton, and her talk is What Happened During the First Half of the India-Asia Collision.
Just advance here. Okay. Thank you everyone for coming. I'm really excited to share our new project that just started in January about what happened during the first half of the India-Asia collision. My collaborator, this is a collaborative research grant from Tectonics, working with Dolores Robinson from the University of Alabama. So the India-Asia collision is the textbook continent-continent collision. It forms the highest mountains on Earth. It is the largest active continental collision. And one of the issues, though, is that we don't, there's still a lot of questions about exactly how and when these two continents collided. So I love this cartoon, but India used to be part of Gondwana. It was right off of the west coast of Australia. And about 130 million years ago, it rifted away and began moving north towards Laurasia as the Neo-Tethys Ocean was subducting. Now, in terms of the timing of collision, there are a lot of different proxies that we can use. We could look at the magmatic record. We could look at plate motions. We could look at marine sediments. But the best way that we found is to look at basically interfingering of these two different continents. So this is a strat column that's showing in blue the Indian sediments, and then in yellow the sediments from Asia. And so when those start interlayering with each other, then we know that there isn't a large ocean basin in between them. And so that's how we date the timing of collision. And so that's at about 60 million years ago. And then collision has been ongoing since then. So if we rewind plate tectonics to about 60 million years ago, we can restore some of the deformation in Asia. And so we have kind of our paleo coastline of Asia. But then India is about 2,600 to 3,400 kilometers away from that. So we have to accommodate that shortening somehow. So we have the large Himalayan range. So this is kind of a great area where we probably have a lot of shortening that's stored up, a lot of kind of according of the crustal material. So it turns out there are a lot of studies that have been done doing balanced cross sections across the Himalayas, and the maximum shortening that we get is about 1,000 kilometers. Which means that we're missing about 1,600 to 2,400 kilometers of shortening. We don't know how that gap was closed. And so this is a major issue in Tibetan tectonics. And there are 3 major models to try to address this. Also, this is about the size of the width of the Arabian Peninsula. So this is a large area that we need to account for. So these 3 different tectonic models, the first is that this was all continental material that either subducted or there's some structures that are hidden that we haven't been able to identify yet. Another model is that the northern part of India actually rifted away, and so we had collision with a microcontinent first, and then we had subduction of another ocean basin. So this would be a 2-stage collision model. And then a similar model is that the southern margin of Asia rifted away and collided with India first. And so then we would have a back arc ocean basin that closes. Some issues are that there's no geologic evidence for an additional subduction zone. But it's also really hard to think of how you would kind of hide or the amount of shortening or even subduct a significant amount of continental crust. So basically, nobody is happy with these models. So if we go back to that 1,000 kilometers of shortening in the Himalayas, those structures started forming about 30 million years ago. So this is kind of telling us about the second half of collision. But the suture zone is actually a lot farther north. And so there's another series, another thrust belt basically of material that called the Tethyan Himalaya that is probably where the record of the first half of the India collision is recorded. But we don't know that much about this area. A lot of, kind of these talks about the amount of shortening this area has been kind of brushed aside as, well, it doesn't have nearly as high mountains or anything, so there's probably not that much there. But we don't actually know. And the Himalaya Karakoram Tectonic Workshop in 2019 identified this lack of information about the Tethyan Himalaya and the missing shortening as the greatest problems in the field of Tibetan tectonics. So this is what we set out to try to address. The star on this map is the location of Everest. And so our plan was to do 2 field seasons with 4 transects across the Tethyan Himalaya. And then we'd be looking at the structure, looking at both major faults, also more kind of mesoscale structures and microstructures as well. And then also looking at the provenance of the sedimentary units, both to be able to correlate them across major structures and also to look for some of the syn-deformational sediments. And then we can use all that structural information to make balanced cross sections. We can restore those and figure out the amount of shortening. Now, this is where a lot of studies would stop. And so the 2 things that we're doing in addition is we're doing thermochronology. So this is looking at the temperature history of these rocks, which tells us about their uplift and exhumation. And then we can combine that with our cross sections to do these thermokinematic models and actually try to match both the structures that we see in the field and the temperature history to look at how these systems have been evolving over time during that first 30 million years of collision. So some of the broader impacts of this project, I am a pre-tenure female assistant professor, and my colleague is a mid-career female full professor. So it's been really great working with her to, kind of help me, help show me the ropes through this project. This is also a great professional development opportunity for our students. I'm going to have 2 master's students. There'll be a PhD student at Alabama. And this is a really great opportunity for them to be able to work at NSF supported facilities. And then I also worked extensively with our colleagues in China during my PhD work, and we're able to continue that collaboration with this project. We're also going to be doing about 10 outreach events per year. And this is to increase awareness of geoscience careers and research, but also to give our students an opportunity to be role models and mentors for the community as well. So how are things going? This was submitted in early 2020, and then the pandemic and all the lockdowns took place, and after we were asked about what our COVID plan would be, and then we were awarded the first time around in 2020. However, we weren't able to travel in this past summer in 2021, and summer 2022 is looking a little iffy for international travel, especially with this new Omicron variant. So we've been working with our NSF program officer on extensions. We had already planned on taking a 1-year no-cost extension. So just kind of, keeping an eye on things as we try to move forward. So some of the lessons that I learned while putting this together is it was really important to be able to reference that workshop that identified these major problems. And then we also had the experience in our team to be able to address this. So my colleague had worked extensively in the Himalayas, and I've worked on the suture zone and looking at kind of the initiation of India-Asia collision. So we're basically able to kind of meet in the middle on this project. Networking was really important. I actually met my colleague at this workshop, and especially those really small and really focused events are really great for making good connections with people. You can be talking to somebody over dinner or on a bus ride, on a field trip. And so you're just really able to, talk with and meet with people in a more meaningful way. It was also really helpful to work with Dolores, who had several NSF grants before, is able to kind of mentor me through both the writing the proposal and managing the proposal as we move forward. And I also got great advice from my colleagues at the CSU who have gotten NSF grants. And so that was really helpful to understand kind of some of the campus specifics of what I needed to incorporate. And then, of course, the grants office was hugely helpful in making sure that everything was really squared away, that the budget was incorporated everything that it needed to, and everything was just kind of neatly wrapped up. Another thing is that the population of students that we have in the CSU is really a strength. These are the types of students from historically underrepresented groups in the geosciences that NSF is really interested in funding, and they're already at our institutions. Also, it was really important for me to make sure that I had another project going. So I was able to, during the pandemic, start a project in Northern California and be able to use some of those smaller internal grants. And so, even though I was able to get a large NSF grant, at the moment I haven't been able to do anything with it because we haven't been able to travel. So, these smaller grants are really great for kind of tiding you over as you're trying to get funded, but also in case of unforeseen circumstances like a global pandemic. So that was really helpful to be able to have those kind of parallel projects. And then with that, I will answer any questions. Thank you so much.
Thank you, Kate, for an interesting presentation. Certainly, given the distance where you actually have your collaboration, the question that kind of shouts out there is how did your collaboration begin? And certainly, you've already stated what some of the challenges have been to sustain it. But what do you foresee might be some of the solutions in sustaining it going forward?
Yeah, so the workshop was where I really met Dolores and was able to really talk through our different interests, things that we were thinking about as major problems, and so then she contacted me in the fall to start working on this proposal, and so we've been emailing a lot back and forth. Obviously now with Zoom, we can do video conferencing basically. And so going forward, I think, some of the things that may come up is we did kind of separate out on what sort of our role in the grant was. So since I have worked in Tibet before, I'm doing a lot of the sort of on the ground logistics in Tibet. And she's doing some more of the lab work once we get back. And so, just kind of coordinating, making sure that, everything from both of our institutions is taken care of for travel, and then, being able to share those results effectively as we get those going forward.
Great presentation, and good luck to you going forward in your research.
Thank you.
Our next speaker is Amelia Vankaran from Sac State, combating climate change with mantle rocks and developing a cross-CSU undergraduate hydrology research experience.
Thank you, Frank. I'm excited today to be talking to you about 2 NSF grants that I had funded this year. I'd like to first acknowledge both the funding organizations that have supported this work and my co-PIs, without which this would not be feasible. So NSF, obviously, and then also several CSU funding sources, including the STEMnet Faculty Seed Grant, the COAST Grant Development Program, and a Sacramento State IDEA program. The first grant I'd like to talk to you about is a basic science grant looking at constraining mantle rock alteration timescales using groundwater ages. This is through the Geobiology and Low Temperature Geochemistry program, and it's also jointly funded through the Hydrology program. The premise of this grant is looking at the chemical alteration of mantle rock by groundwater, where CO2 is dissolving into the water, partially dissolving that rock, and then as it also hydrates, producing hydrogen gas, which is an energy source for chemosynthetic microorganisms in this environment. This research is focusing on CO2 mineralization to combat climate change. So taking carbon dioxide out of the air and storing it in the form of carbonate minerals for permanent and safe storage. So that involves carbon dioxide dissolution into water, then dissolution of these mantle rocks in order to produce ions like calcium and magnesium that can then bind with that dissolved carbon to create carbonate minerals like calcite and magnesite, which again are safe and permanent storage mechanisms. So you don't have to worry about the CO2 escaping like in traditional conventional geologic CO2 storage. In Oman, where I have my field site, this occurs in two different aquifers. There's a shallow aquifer where the groundwater is in communication with the atmosphere and can be continually absorbing carbon dioxide. There you also have continual mantle rock dissolution and addition of the magnesium ions to form the magnesite in the shallow surface. And then at depth, where the water is cut off from the atmosphere, instead of carbonation, there's serpentinization, so we're hydrating that mantle rock to form serpentine. That also causes the water to become pH about 11 or 12, so hyperalkaline, and to accumulate calcium. And then when that water comes back to the surface, it rapidly absorbs carbon dioxide from the air and can also mix with shallow groundwater containing carbon dioxide to form more carbonate minerals. So there's storage at many different locations along this groundwater flow path. The problem is we don't understand how long this process takes. There are estimates ranging from 500 to 200,000 years. So one question is how much CO2 can you actually store down there? And that will depend on how much reactive surface area of the rock is available, whether the open surfaces of the rock get armored by the formation of the serpentine and these carbonate minerals. So there are questions about how much CO2 could actually be stored, and then also how fast just the natural processes happen and how much hydrogen is generated by them. So the serpentinization process also produces hydrogen gas, which is a chemical energy source for life in this extreme environment, and also is thought to have been the source for early life on Earth and potentially elsewhere in the solar system like Mars, Europa, and Enceladus. So really interdisciplinary outcomes or of interest. This project is helped out by the Oman Drilling Project, which has over 200 scientists studying many different aspects. These mantle rocks are globally distributed. They have a huge CO2 storage capacity, enough to store over 1,000 years worth of anthropogenic carbon dioxide emissions. But whether or not that's actually feasible is another question. And California does also have these rocks, including some near carbon dioxide sources. So this map is showing carbon dioxide sources in California, primarily from electricity generation. And if we overlay the mantle rock locations, the black blobs, there are several locations where they are co-located. So my grant is specifically looking at the timescale of these natural chemical reactions and trying to get at that by using groundwater ages, with the idea that the groundwater is interacting with the rock, and if we can get a time scale for how long it takes to alter the groundwater to this pH 11 or 12 composition, we have a maximum time frame for how long those chemical reactions take. So we'll be using a number of different environmental tracers to do that, and also looking at the source of hydrogen in the groundwater. Some of this water is so gassy you can actually light it on fire. But the question is that hydrogen caused by ongoing low temperature alteration? Is it a relic of high temperature alteration when this rock was at the seafloor? Or has it been transported up through from another rock formation? So how we'll address this problem is to date the groundwater using a range of environmental tracers. So including tritium, argon-39, carbon-14, krypton-81, and stable noble gases like helium-4. And so this will allow us to determine an age distribution if there's mixing of deep and shallow groundwater. This is a fractured aquifer system, so quite complicated flow dynamics. And I was fortunate enough to be able to do some preliminary research on this in spring 2020, just before COVID shut everything down, with a graduate student from our program. And that was funded by the CSU STEMnet faculty seed grant. And then our second objective is to determine that hydrogen source using hydrogen isotopes, which fractionate according to temperature at the time of formation. And again, this is an international collaboration with scientists from University of Southampton, Columbia University, Montana State University, Colorado School of Mines, University of Colorado. So a really large group of people that includes both hydrogeologists and biologists looking at the range of microorganisms in this environment. The lessons learned from submitting the grant, we don't have many results so far because we just were awarded the grant this summer. But the preliminary research, preliminary data funded by that faculty seed grant was really helpful in making a compelling proposal. Also, it was a collaborative proposal for multiple organizations. Like Kate, I found it really helpful to partner with a senior scientist who had experience submitting proposals. And I also found it helpful just to maintain motivation to have someone to work with. We submitted under the RUI solicitation, which allowed us each an additional 5 pages to describe the impact on the PI careers, department, and institution, and allowed us to justify asking for assign time, which with our workload is key. It did take 2 submissions to get funded, but addressing the reviewers' concerns really allowed us to create a more focused and feasible proposal. So I think it really helped. Actually to have the reviews. The sponsored programs office, our grants office, again, great with edits, read many drafts, and really helped craft a compelling proposal. And both of my efforts were supported by the local Sac State incentive for developing external awards. So that was a monetary incentive, but also very helpful because it provided an external deadline. The proposal that I submitted had a rolling deadline, and it really helped have something force us to pull the trigger and really submit. So that external deadline helped us to actually get it in instead of keep revising. The second project is GeoPath's Undergraduate Preparation Award. So that's developing a diverse hydrology workforce through an undergraduate hydrological research experience in a coastal California watershed. This is a collaboration with 2 other CSUs, including San Diego and Humboldt. And the objective is to recruit and retain a diverse and interdisciplinary group of students to hydrology. So we have a learning ecosystem model where the students spend a year with us. They get a learning community by meeting the other students, get faculty and peer mentoring, and they are engaging in place-based collaborative research. They start with a spring preparatory course, then move on to a field experience, and finally have a fall research and professional development course. So in the spring, they get introduced to the critical zone, they start getting mentored, and they prepare for the field experience so there aren't any surprises once they get there. And they start doing some team building because, again, this is incorporating faculty and students from 3 different CSUs. Then we join all together in person for a summer field experience at the NSF Eel River Critical Zone Observatory, where we can learn about ongoing research, and the students are going to get hands-on experience with hydrology field techniques and collect data that they can use to further that research. And the students are also paid a stipend for participating, so students that need to take off work in order to go can do that. And then finally, in the fall, they take a sustained learning course where they learn research skills using data collected in the summer to answer research questions. So doing hypothesis development, data interpretation, learning science communication skills, and also getting professional development skills like learning about hydrology careers, developing a resume, applying for an internship, and then communicating their science to stakeholders like the Forestry Service partners that we have. So the lessons learned from this grant, again, it was collaborative from multiple institutions. We were fortunate to get 3 units of release time per PI in order to write the proposal. That was funded through the the COAST Grant Development Program. So it was really helpful for us to all, the same semester, have release time to really focus on writing this proposal. And probably because of that, we were able to get funded in the first round. And we did have to be flexible. The program officer came back to us saying they wanted to fund it, but with a 10% budget cut. And so we had to make that work. So to summarize the lessons learned from my 2 different proposals, really focus on the strengths of the CSU. So like other presenters have mentioned, we're often a primarily undergraduate institution, which allows us to submit under that RUI solicitation, and we can often have many and strong broader impacts due to the diverse population of the campuses. Find good collaborators, particularly senior ones if you're a junior faculty. Talk to the PO before submission. I was able to do that in person at an NSF Grants conference. That was great. Also, be willing to revise and resubmit. Don't take that no as a no. Take it as a here's how you should improve it. And have your sponsored programs office help with that. Attend writing workshops. And I recommend that internal funding to really help support your proposal development. It's a lot of work, and it helps if you can get some release time or incentive to do that. And with that, I'd be happy to take any questions.
Thanks, Amelia, for a great talk. And certainly if any NSF program officer would come to me and say, we'll fund it if you cut your budget by 10%, I would jump on that like that. Okay. So quick question, what kind of broader impacts did you include, and how did being at a CSU shape those?
Mm-hmm. Yeah, for the GeoPaths hydrology one, it's essentially all broader impacts, right? A course-based undergraduate research experience, high impact practice, trying to recruit more diverse students to hydrology. So we have actually some pretty focused recruiting techniques to access other students who might not be exposed to hydrology originally. And then for the Oman mantle rock alteration, what we did was focus on funding the undergraduate student research so that a diverse group of students can participate, and also to incorporate, again, the course-based undergraduate research experiences. So we're developing a kind of a case study looking at the research to present in our own classes, and then we'll post those to that CERC, the Science Education Resource Center at Carleton College, so that other faculty can use it in their hydrogeology courses in the future. Again, that diverse student body at Sac State allows us to engage students who traditionally are not involved in the geosciences in the research. And we're also building groundwater tanks to illustrate carbon dioxide storage through mineralization to use as a demonstration tool in classes.
Great, thanks Amelia, and really thanks to everyone here for your wonderful presentations. You all did a fabulous job, as always. Speaker contact information is provided here. For more information on any of the presentations, please contact them, as it may lead to a collaboration or a proposal opportunity. In addition, a link to this webcast will soon be made available on the STEMnet website. For more information on this, please contact Monica Lacone or myself, and previous webcasts can be found on our website. STEMnet is always looking to collaborate and write multi-campus proposals with faculty. In fact, we've submitted over 26 over the past 18 months, partnering with 15 CSU institutions, and I'm happy to say more than half of these have been funded. So if you have an idea and would like to chat about a project, please send me an email. And finally, December is here and the holidays are upon us, and while the world continues to battle against a formidable foe, COVID, we can say with some solace that this holiday season will be a safer one than our experience a year ago. Still, we are some time away from whatever our new normal will eventually be. Moving forward, what we can do is do the right thing by following proper safety protocols, vaccinate, wear masks when appropriate, and believe that working together as a community will help us through these difficult times faster, easier, and with a smile. Although our next webcast will not be until February 4th, STEMnet will continue our work in December and January. We have a number of collaborative proposals due next month with faculty from across our system, and still others in preliminary stages due in the spring term. Besides our planned series of webcasts beginning in February, we also have our monthly virtual research cafe and other activities. All these events will be publicized, so stay tuned. Finally, to all of you, have a great weekend, and I'll turn it over to our own Jennifer Wicks for a few closing remarks.
Thank you very much, Frank. Wanted to just let everyone know we do have the webcast feedback survey. We would love to hear from you. If you could use your telephone, your telephone sounds like a funny dated word now, doesn't it? Use your cell phone and just hold it up to the QR code. It'll take you right to the survey. Thanks to Monica Alarcón for setting this up. As well, you can join our CSU STEMnet community listserv. You can actually click on the link that's on the left side of your screen on the PowerPoint there. Also, we do have the private CSU STEMnet Facebook group. Would love your participation in there as well, and you can click on that hot link as well on the slide. And Monica's actually pasting those links in, so I'll go ahead and advance the slide to the next one. She'll put the links in the open chat for you. Any information you'd like to find out about the STEMnet group organization at the CO across the system, you can click on that QR code there on the screen and it'll take you straight to where you can find all the recordings, several presentations, and information and resources. So we want to wrap today, send everyone off into a wonderful weekend, and thank each of our experts for joining us for their presentations today and for sharing. And of course, Dr. Gomez and Monica Alarcón and our production assistant, Kayla Perez, behind the scenes. Thanks to everyone. And we look forward to seeing you on our next session very soon. Have a great rest of the day, everyone. Take care.